So we come to the next section, which is about conservation of linear momentum. We know what momentum is. It's mass times velocity, right? So if you have an isolated system, that means a system where all the interacting objects are inside the system. There is no interaction with the outside, no energy or can be lost or received. Okay, so all the interactions that happen in the system must be inside. For example, if you have two objects that are going to collide, they are both within the system. Okay, so that's called an isolated system. Remember, we also talked about an isolated system in terms of energy when we looked at the previous chapter. Okay, so momentum in an isolated system in which a collision occurs is always conserved. The linear momentum is conserved. Okay, the collision may be a physical collision, or the objects may simply come close to each other and have sort of electrostatic contact. Okay, in your case, it will always be a physical contact. Okay, so you'll have actual masses which collide with each other. There can then be no external forces. That means all the forces have to be within the system. Yeah, they have to be internal to the system. Okay. So the principle of conservation of momentum, let's read the green part. It says the total momentum before the collision will be equal to the total momentum after collision. This is the magnitude of the momentum. Okay, it's going to be the same number. That's just like in energy conservation. The same amount has to be there initially, and the same number, same magnitude has to be there finally. Momentum of each object may change. Okay, so it's just for the total system that the momentum has to be conserved. The distribution of momentum between the two objects, say 80-20, 50-50, 20-80, these could change before and after. Yeah. So mathematically, we have some initial momentum. Let's write that as, if I have some initial total momentum for the system, it must equal final total momentum for the system. Okay? And these are vectors, so we can write the vectors quantities. I'm going to split this out. Let's say we have two objects, mass m1 and m2, each having some initial velocity, v1 initial and v2 initial. Okay, so here are my two objects. And let's say for the sake of convenience that they're moving towards each other. Does not have to be the case. I'm just making them of different masses. So let's say this is m1 traveling initially with some velocity v1 initial. And this is mass m2 traveling with some initial velocity v2 initial. So this is before collision. And after collision, a number of things may happen. Okay. So let's again assume that m1 continues in this direction. Okay. So we have m1 now moving with a velocity v1 final, and we have m2, and let's say this also starts moving this way. We don't know which way it moves, but we are going to just assume a direction. Okay, m2, v2 final. So this is my picture after collision. This is my picture before collision. And I'm saying the total momentum here for this isolated system must equal the total momentum here for this isolated system. That's what this equation represents. So this is the initial part, m1, v1 initial. This is my initial momentum of the first object plus initial momentum of the second object equals the sum of the momentums for the two objects finally. Yeah, that's, so here we have a mathematical equation that represents our system. So from the conservation of linear momentum, we actually now have a relationship between a before and after of the system. Yeah, before and after collision. During the collision, object 1 is interacting with object 2 via a force, and object 2 is interacting with object 1 via an equal and opposite force. Remember, we know from Newton's laws that if one object pushes on the other, then instantaneously the second object is pushing back on the first one with an equal magnitude and opposite in direction. So if this represents the force that F1 experiences due to object 2, okay, object 1 experiences, then object 2 experiences a force due to object 1, which is equal and opposite. At every point, it's equal in magnitude at any given time, and it's opposite in direction. So if this is positive F, this is negative F.